All right, I think we're feeling pretty good about evaluating these limits. Let's keep going. Let's see how far we can go with this technique here. So in part A, I have limit as x approaches -3. I've got this rational function, and if we're not sure where to start, I'm going to try taking that number. Let's plug it in. Let's see what happens. If I get back a real number, that's my limit. That's my solution. So let's see, I have -3 squared plus 4 times -3 plus 3 all over -3 plus 3. So let's see, I've got 9 minus 12 plus 3 divided by, oh boy, 0. 9 minus 12 would be -3 plus 3 would be, oh boy, 0 over 0. Now, we said earlier, in an earlier example, we said when you were looking at the value of the function and you end up with 0 divided by 0, that the function is undefined there. But that's not the same as saying that the limit is undefined there. Remember that those two can be two different things, right? The value of the function is different than the value of the limit. So right now, I don't really know what to do with 0 divided by 0. So let's try something else. We may need to go back and think about, well, what else can we do with this? So if I think about this, limits as x approaches -3, I'm mostly interested in this numerator right here. I'm going to think about, okay, is there any way that I can kind of manipulate this or rewrite it so that it's a little bit easier to work with? So here I've got x squared plus 4x plus 3. I say, okay, well, that's a quadratic. Let's try factoring it. So let's see if we can come up with two numbers that multiply to be 3 and add to be 4. So those, of course, would be x plus 3 times x plus 1, and then in my denominator I still have that x plus 3. Okay, so I feel like we're getting somewhere. Now I see, okay, we've got an x plus 3 in the numerator, x plus 3 in the denominator. Those two can cancel. So if I think about this simplified version of my function, this limit as x approaches -3 of x plus 1. So let's try plugging this in now. Let's see if we get a different answer this time. I think we will. So -3 plus 1 equals -2, and hey, there's my limit. So okay, if we end up with something like 0 over 0, then maybe we need to rewrite it, and we can factor it. But it looks like the limit's going to exist here. So let's keep going with that. Let's see what happens. So in part B here, I've got another function. I've got limit as x approaches 4. I've got x squared minus 16 over absolute value of x minus 4. So, hey, let's take this 4. Let's plug this in for x. Let's see where we go. 4 squared minus 16 all over absolute value 4 minus 4. Oh, let's see. 4 squared would be 16 minus 16 over absolute value of 0. This is, oh boy. Well, who could have seen that coming? All right, well, 0 over 0, that doesn't really tell me anything for right now. I need to think about a different approach to this problem. So I might say, okay, right, we tried factoring the last problem. Like, we could try factoring here too. And if you wanted to graph this function, I would actually say, yeah, I think factoring is probably a good way to go. So I could say, okay, limits as x approaches 4. I've got a difference of 2 squares in my numerator, so that's x plus 4 times x minus 4 divided by absolute value of x minus 4. Now, you might want to say, hey, look at this, Mr. H.A., look at this. I've got x minus 4 in my numerator and absolute value of x minus 4 in my denominator. I can just cancel those out just like I did last time. And I would say, well, not quite. The absolute value causes some problems. And if you wanted to, you could graph this function. And honestly, I think that's probably the way I would suggest this here, is I might take some numbers and plug those in. I might say, well, let's plug in numbers that are close to 4, right? So we're interested in the behavior around 4. So I might say, okay, let's take, how about we take x equals 5 and plug that in. So 5 plus 5 times 5 minus 4 over absolute value 5 minus 4, and then go and kind of figure out what that's going to be, and you'll end up with a y value here, and then you can take that, and so you'd have a point at 1, 2, 3, 4, 5, somewhere over here. But I'm lazy and impatient, and I just don't really feel like graphing this right now. So what I will do here in this case is we have other tools at our disposal, right? We can use technology here. So I'm going to go ahead and graph this, and in fact I already have. Let me go ahead and throw that in here. So here is the graph of this function. Oops, don't want to give away the punchline here. So here's the graph of this function. It's in blue. And so I want to know the limit as x approaches 4. And if we have the graph, I think it's a whole lot easier. So, okay, here we've got x equals 4. Remember, the two-sided limit only exists if the left-hand limit is equal to the right-hand limit. Well, if I look at the left-hand side of 4, if I say, okay, where is the left-hand side of my function approaching? Looks like it's approaching a y value of -8. So the limit as x approaches 4 from the left-hand side of x squared minus 16 over absolute x minus 4 is equal to -8. But if I wanted to look on the right-hand side, limit as x approaches 4 from the right-hand side, x squared minus 16 over absolute x minus 4. So if I approach 4 from the right-hand side over here, this time it looks like I'm approaching a y value of +8. And you might have been able to look at the graph and just sort of see where we're going with this. And okay, because these two don't agree, right? They're not the same number. -8 is a different number than +8. That means that the limit as x approaches 4 of x squared minus 16 over absolute value x minus 4, does not exist. Does not exist because those two, the left-hand limit is different than the right-hand limit. I ended up with two different numbers. So the thing I want to highlight in these two problems is both of these cases, when we just started off the problem and you said, let's just take that number and plug it in, we ended up with 0 over 0 here. And in the second problem, we also ended up with 0 over 0. But there's a really big difference I want to point at. In the first problem, we had 0 over 0. Our limit ended up being -2, so our limit did exist. But in the second problem, when we looked at that limit, we looked at the two one-sided limits here, that limit did not exist. So this form 0 over 0 that we ended up with, it has its own special name. So here's the definition and a couple things we need to talk about. It says we say that a limit is indeterminate or of indeterminate form if the limit as x approaches c of f of x equals 0 over 0. So be very careful with these because these limits may or may not exist. If you have an indeterminate form, you need to go back and try to simplify. So if on a homework assignment, a quiz, or exam, you say that limit is 0 over 0, you cannot say it's indeterminate. That doesn't really mean anything to me. You can't just assume that that limit does not exist. You also just can't, make up your own limit. You can't just say, well, it's, 0. You have to go back and you need to try to simplify. The number one way I'm going to suggest simplifying is factoring. You might see, I can't remember, I think it's in my other class, my Calculus 1 class, we do a little bit of work with the conjugate, but 99% of the time, these problems are going to boil down to let's try to factor it and then work with that factored form. And so this theorem right here is kind of where we might get a little bit confused, but it's an important distinction to make. It says the limit as x approaches c, if you have f of x over g of x and you end up with L divided by 0, that limit does not exist if L, there's a really important typo there, if L is not equal to 0. So if you end up with like 1 divided by 0 or -4 divided by 0 or negative 0.5 over 0, any real number divided by 0, that limit does not exist. So if you have 0 over 0, If you have 0 over 0, that's indeterminate form, in which case your limit might exist. We don't really know. We don't have enough evidence just by looking at that. That really means you've got some more work to do. Go back and try something else. But if you take that number and plug it in, L divided by 0, that limit does not exist. So if you end up with a constant, any other number other than 0 in your numerator and a 0 in your denominator, that limit will not exist. So let's look at a couple of examples here just to kind of understand the difference between these two things. So in part A here, I've got limit as x approaches 3, x minus 3 over x plus 3. Let's take 3, let's plug it in for x here. So 3 minus 3 over 3 plus 3. 3 minus 3 is 0, over 3 plus 3 is 6. And here I will say this is a trick question, because 0 divided by 6, if I go back and look, that's certainly not 0 over 0, and it's also not L divided by 0. I am trying to trick you here. If you end up with 0 in your numerator and a constant in your denominator, this is simply just 0. So be careful about these types of expressions. Next up, we've got limit as x approaches 3 of x minus 3 over x squared minus 9. So if I try to take 3 and plug that in, 3 minus 3 over 3 squared minus 9, I have 0 over 9 minus 9, 0 over 0. So I have indeterminate form here, which means I need to go back, I need to try something else. So some of you might have seen it right from the get-go. You might have said, hey, look at that denominator. That's a difference of 2 squares. We can factor that. So limit as x approaches 3, x minus 3 all over x plus 3 times x minus 3. If we factor that denominator, then we've then got that common factor of x minus 3 in the numerator and the denominator. So I'm really looking at limit as x approaches 3 of 1 over x plus 3. So let's take 3, let's plug this in for x now. Let's see if we get back an answer. 1 over 3 plus 3, this is 1 over 6. Hey, there's my limit. So again, if you plug something in, you end up with 0 divided by 0, you need to go back and try something else. You need to factor it, simplify it somehow, check the graph of the function perhaps, but you need to look at something. Last case right here, C. Part C right here, I've got the limit as x approaches 3, x squared plus 9 over x minus 3. Again, I am trying to trick you right here. Be careful with this guy, x squared plus 9. You might say, hey, that's a difference of 2 squares, but no, it's not. Here I have x squared minus 9. That's way different than x squared plus 9. If you have x squared plus 9, that cannot be factored. That is what we call a prime polynomial. I can't factor it. So let's just take x equals 3, let's plug it in, let's see what happens. So 3 squared plus 9 all over 3 minus 3. So I've got 9 plus 9 over 0, or 18 divided by 0. For now, we see that this limit does not exist. When we get into the next section, we are going to talk a little bit more about limits that end up looking like this form. It turns out there is a little bit more that we can say about them, but for now we're just going to say, you know what, this limit does not exist because I have 0 in the denominator but not in the numerator. So please, as you're working through these example problems, try and pay attention to, do we have a limit that is of indeterminate form, or do we have a limit that does not exist? Because they look very, very similar, but we handle them in very different ways.